Hi, my name is Dilara Abdel and I'm a PhD student at the Weierstrass Institute in Berlin. First of all, I want to thank the organizers for the opportunity to give the optoelectronic device community an insight into my work. The topic for today are finite volume discretization methods for solving the semiconductor device equations. And one ingredient for such a method is the proper choice of flux approximation. So the aim of this talk now is to compare and analyze aspects of two state-of-the-art modified Scharfetter-Gummel schemes. And before starting, I want to thank my supervisor Patrizio Farrell and our colleague Jürgen Fuhrmann, who collaborated on this topic with me. In the first step, I'm going to present the examined system. With the help of these semiconductor device equations, it is possible to simulate current flows in semiconductor devices. The unknowns are given by the electrostatic potential and the charge carrier densities for electrons and holes. We have a Poisson equation which is coupled to two continuity equations. The current densities here are given by a composite of the drift from charged species caused by an electric field and the diffusion of free electrons in holes. The carrier densities are defined with a function f, which is called statistics or distribution, and the argument of this function is dependent on the electric and the quasi-Fermi potential. A useful relation which we need is the generalized Einstein relation, which connects occurring physical quantities in the current densities. And to be more precise, with help of the diffusion enhancement, we can rewrite the diffusivities dN and dP. And inserting this reformulation now in the flux expressions shows the nonlinearity in the diffusive part of the current densities. Something which was not discussed yet is the choice of statistics function. And for modeling inorganic semiconductor devices, the Fermi-Dirac integral of order 1/2 is used as distribution. And suitable approximations of this integral are the Boltzmann and the Blakeman statistics. The Boltzmann statistics is used for modeling non-degenerate semiconductor devices. Concentrating now here on the figure, we see that for large negative arguments, all functions nearly coincide. And in this area, the nonlinear diffusivity here vanishes due to the definition of the diffusion enhancement, and thus physics and the numerics in this area is well analyzed. Contrarily, for large positive arguments, the physics and the numerics behind the van Roosbroeck system is more complex, and this can be again explained by the diffusion enhancement, since the occurrence of this function causes an increase of the nonlinear diffusivity in the current densities. In the next step, I want to talk about the derivation of the discrete system and introduce the different flux approximation. We exclusively dealt with the Voronoi finite volume discretization method. After applying the common steps of a finite volume discretization method to our charge transport model, we receive this fully discretized finite volume system. And the crucial question in this talk now is how to choose these two current densities in red. We want the flux approximation which is numerical stable and preserve physical properties of the continuous system, such as thermodynamic consistency. And the approach of Scharfetter and Gummel satisfies these conditions. Their idea is based on the assumption that these discrete current densities and the electrical field are constant along each edge of the control volume. Then the flux is projected onto the shared phase between two control volumes, as depicted here in the figure. In case of the electron current density, we receive this ordinary differential equation. If assuming a Boltzmann relation, this two-point boundary value problem can be solved explicitly, since the diffusion enhancement equals 1. We receive this flux discretization scheme with B as the Bernoulli function, which is also shown here. Now, this This idea of Scharfetter-Gummel can be extended to arbitrary statistics F, but the problem is that this generalized two-point boundary value problem is then in general not explicitly solvable. However, Kuprucki and Gärtner showed in case of the Blakemore statistics that this two-point boundary value problem can be simplified to an implicit equation for the discrete current density, which can be solved within few Newton steps. But the problem here is that in some applications we need to avoid this increase of computational costs when applying a Newton solver, and hence computational less expensive flux discretization schemes are needed as an alternative. And two of such thermodynamically consistent modified Scharfetter-Gummel schemes will be introduced in the following. The earliest reference we could find for the first scheme is a software package called MM03 developed by colleagues from the Stanford University in the 80s. Therefore, we will call this scheme the Zidin scheme. A special aspect here is that there are comparisons of the device simulator itself available with other simulation tools, but there are barely comparisons of this flux discretization scheme with other schemes known in the literature. The idea of this scheme is based on extending here the drift part by the excess chemical potential and then solving the projected equation. The other scheme which we will discuss is the diffusion enhanced scheme by Bessemola-Chattard, where the idea is based on logarithmically averaging the diffusion enhancement. Notable here is that in case of a denominator near zero, regularization strategies need to be developed to handle this removable singularity. Finally, we cover now the main part of this talk, the comparison of the flux approximations. And there is a paper of my two collaborators with Thomas Kuprucki where the diffusion enhanced scheme and other modified Scharfetter-Gummel schemes were already compared to the generalized Scharfetter-Gummel scheme. There, the Taylor expansions and the corresponding error estimates of the schemes were derived, the errors in the local flux approximations were visualized, and finally a pin device was simulated. These methods of examination were now also performed for the Zidin flux approximation, and selected results will be now shown here. Notable is that we used the Voronoi finite volume PDE solver in Julia written by Jürgen Vormann, and a comprehensive overview of this package can also be found on YouTube. So, in the first step of comparison, we derived Taylor expansions of this form. And the absolute errors here in the prefactors alpha I between the modified schemes and the generalized Scharfetter-Gummel scheme were computed and visualized for the Blakemore statistics. For large negative arguments of the statistics, we know that the Blakemore and the Boltzmann statistics nearly coincide, and hence the modified Scharfetter-Gummel schemes converge towards the generalized Scharfetter-Gummel scheme. And this is why we observed nearly vanishing errors in this area. Contrarily, for large positive arguments, we see that the error corresponding to the diffusion enhanced scheme here in blue increases for a greater order of the perturbation in the argument of the statistics, whereas the error corresponding to the Zidin scheme nearly vanishes. And this gives rise to think that in case of a vanishing electrical field, the Zidin flux approximation holds more advantages. Nonetheless, these figures show that none of the modified schemes is third-order accurate, and hence second-order error estimates for the local flux approximations were derived. We see that that the occurrence of this additional summand in the error estimate for the Zidin flux approximation suggests a better performance of the diffusion enhanced scheme. So for a far-reaching comparison now, we visualize in the next step the errors in the local flux approximations. And for this, we consider two different fixed values for the averaged argument for the average argument of the statistics, which also occurs here in the prefactors. We are here in the degenerated case where we use the Blakemore statistics. This means that we can use the Kuprocki-Gärtner flux as a reference solution for the generalized Scharfetter-Gummel scheme. The logarithmic absolute error between the modified schemes and this reference solution are now depicted here in dependence of the perturbation in the electrostatic potential and in the perturbation in the argument of the statistics. The dashed lines here correspond to areas where the schemes coincide due to previous considerations. We see that increasing the maximum error here in the evaluation point results in a larger area where the modified schemes coincide with the generalized scheme. And this can be explained by the previously seen error estimates where the derivative of the Blakemore statistic enters, which decreases for large positive arguments. Additionally, what we can observe here is that considering the Zidane scheme, it seems that this scheme is exact for a vanishing electrical field. That means along this red dashed line. And this observation could be analytically proven in our work. This means that in case of a purely diffusive flux and a model based on the Blakemore statistics, the Zidane scheme seems to be the best alternative flux approximation. So in the last step of comparison, we simulated a gallium arsenide pin device in the degenerated case. And we have n nodes dependent on a refinement level for each region. And we considered the stationary drift diffusion model with homogeneous Dirichlet-Neumann boundary conditions. The computed total currents for refinement level 1 and 3 are depicted here dependent on the applied voltage. The reference solution in blue was computed using the Kuprocki-Gärtner flux on a refinement level 10. We see that none of the computed total currents is exact, but they are already quite accurate on a refinement level 3. Concentrating here on this figure, we see that the diffusion-enhanced scheme seems to be less favorable. Nevertheless, the IV curves do not coincide here in general, and hence the L-infinity errors in the computed total currents for the first 9 refinement levels are shown here in dependence of the mesh width. We see that all errors converge with an order h square and that they behave quite similar. Focusing here on small refinement level, that means on coarse meshes, it seems that the Zidane scheme is as exact as the generalized Scharfetter-Gummel scheme. And this is notable since coarse meshes play a role in three-dimensional simulations where computational resources are limited. So to sum up briefly now discussion made in this talk, we introduced 2 thermodynamically consistent modified Scharfetter-Gummel schemes and compared them. We saw that we can derive the sharpest error bound for the diffusion-enhanced scheme, but need to be aware that considering the implementation, the scheme needs to be regularized. For the Zidane scheme, we found out that this scheme is exact for purely diffusive flux and a model based on the Blakemore statistics. Also, the simulation of the pin device indicates that, especially on coarse meshes, the Zidane scheme seems to be a good alternative to a computational expensive flux discretization scheme. So now, with this work made as a fundament for future research, we want to extend the code used here for the simulation to a prototype drift diffusion solver based on the programming language Julia. Also, we are interested in the simulation of multidimensional problems and further applications, also for a possible extensive discussion of the introduced flux approximations. So suggestions for further applications are welcomed. This is now the end of my talk. I thank you for your attention, and if there are any questions, do not hesitate to send them to me. I will answer them during the conference. So again, thank you.